Now we will see the transients in a synchronous generator. So what is this transients and why is studying them important? So if you remember transients, you must have first heard in networks, right? So let us take a DC source connected to an RL load via a switch. Okay. Now initially when the switch is open, there is no current flowing. But right after the switch is closed, what will happen if you consider the current? Then the expression is going to be Vs by R, where Vs is the DC source, R is the resistance, into 1 minus e to the power minus t by tau. Okay. So where tau is the time constant, L by R. So L is the inductance. Now when you plot I of t as a function of t, what are you going to get? It will initially rise and then it will become constant at what value? Vs by R. Okay, because t is equal to infinity, if you substitute I of t, you are going to get Vs by R. Okay, so now this part that you have here, this is the transient, that is before this time. After this time, it is a steady state value. It is not changing. It has sort of reached a constant state. Okay. So this is the transient that we see in networks. Similarly, when you have a generator and this is supplying a load. Okay. So if you see as an electrical circuit, this is not very different from this. This is also a generating source. It is giving you a voltage. This is also a voltage source. And this is an RL load you can consider. Whatever we have here, it can be in the form of an RL load. So now similarly, when there is a change in the load or when there is a change in the input, the mechanical input to the generator, then there are going to be transients. Any change in the network is going to give rise to a transient state, and after the transient, it will eventually settle back onto a steady state. Now, why is studying that transient important? Because transient is related to the stability of the operation. In power systems, we have power as a function of the torque angle. Okay, so in that case, this is going to be the expression, the relation between P and delta. Now this peak here, this is called as the steady state stability limit. So that means theoretically the generator can give this amount of power. Okay, but we never operate at this point. The reason is that whenever there is a transient, then this will immediately go out of synchronism. That means it will fall out of sync with the grid. Okay, so now you will operate somewhere here. Okay, usually operated somewhere here. Now when a disturbance occurs, then what will happen? The generator will oscillate about this point. It will go like this and then come back and then oscillate about, either it will settle down at this original state, otherwise if the conditions of disturbance are different, then it might settle down at a new place, new point. Okay, so we have to see how far it is oscillating. When it is going beyond the operating point, how far is it going? If it is operating at this point, then this will be the limit. Okay, but if it is operating at this point, then the point can go slightly here. During transient, it can go beyond the steady state limit. Okay, so that will be understood when you are studying power system stability, equal area criterion. Okay, but for now it is enough to understand that this is the steady state limit, but we never operate here, because in case of a transient, it will fall out of synchronism. It will not be a stable operating system. So we will operate somewhere here so that it is allowed to have transient. Okay, so that is why it is important to study transients, because it is related to the stability of the system. Okay, so once we have understood that studying transient is important, next is what are the kind of transients that can occur. Okay, So load changes is one kind of transient, and there is a change in mechanical input. So that means we have a prime mover which is driving the rotor. If there is a change in that, then there is going to be a transient. Okay. But the most severe kind of transients you will see in case of a fault. Specifically a three-phase symmetrical fault. So what will happen in a three-phase symmetrical fault? All three lines are going to be shorted. Okay. There will be a fault wherein only a single line is shorted, double line is shorted, or maybe two lines are going to be shorted. But this three-phase symmetrical fault is where all three lines are being shorted to the ground. So this is called as a three-phase symmetrical fault. So since this is the most severe change that can occur, we are going to study this three-phase symmetrical fault, the transients that are occurring due to this three-phase symmetrical fault. Short circuit transients. So initially the currents that will be flowing in each of the phases, let us say it is IA in phase A, and in phase B it is IB, and in phase C it is IC. If you consider the per phase equivalent circuit, then there will be armature resistance, synchronous reactance, which will be delivering power to the load. Right? Now a fault has occurred here. Okay. So now the load is short circuited. Now what happens? The current through the inductor, it cannot change instantaneously, right? So before fault occurs, only AC component was present. Okay. But after the fault occurs, now there is a huge amount of current that needs to flow because the load is being short circuited. So the AC component has to increase, but the total current through the inductor, it should remain the same. So there will be a DC component that is introduced. Okay. DC plus AC component. Okay. So why is that? You can write the fault will result in high AC component, but current through inductor cannot change instantaneously. So DC component comes into picture. Okay. So this is the reason why you will be seeing a DC component after the fault in a synchronous generator. So how will the currents look like after the fault? In each of the three phases, you are going to have currents like this. So you can see that there is a DC component, the dotted part here. Similarly, for phase B, you have a DC component. Phase C also you have a DC component. And they are all having different phases, so that the phasor sum of all these currents, eventually it should be 0 because it is a three-phase symmetrical fault. Okay. So this DC component will ensure that the total sum, that is the DC component plus the AC component, it will be equal to the current that was flowing through the inductor or the machine before the fault occurs. And one more important thing that you can see here is it is reducing with time. The DC components in all three phases, it will reduce with time because it is a transient. Okay. So now if you consider only the AC component, the symmetrical AC component, then it is going to look like this. Okay. So you can write it down here. The symmetrical AC component. So initially it is going to have a very high magnitude and then it will reduce. Okay. So now what is happening here? Initially, why do we have such high magnitude of current, and eventually why is it reducing? See, remember, this is in the steady state, it doesn't mean that the fault is being cleared. The steady state means that the steady state current that is flowing during the fault. Okay. So the steady state of the fault current. So now we will understand why it has three distinct phases: subtransient period, transient period and steady state period. We have something called as the damper winding, and of course we have the field circuit. Okay. Now what is this damper winding? We will discuss it a little more in detail later, but for now you need to know that this winding, it will ensure the stability of the machine. Okay. It will ensure that in case of any transients, in case of any kind of disturbances, the machine is continuing to run at synchronous machine. Okay. This is used to maintain stability. So this is the case of synchronous generator. In a synchronous motor, damper winding is also used for starting of the machine. Okay. Now what will happen? Initially, right after the fault, there are going to be currents induced in the damper winding as well as the field circuit. Okay. Now when the currents are induced, what will happen? There will be a resultant flux. So you are going to see an increase in the internal generated voltage. Okay. So you can write this point down. Due to currents being induced in damper and field windings right after the fault, the internal generated voltage will increase, or it will be very high. So once the internal generated voltage increases, then what will happen? The current will be very, very high for the same fault impedance. Remember, when the short circuit is occurring, the impedance is not changing, right? But the internal generated voltage is very, very high initially. So that is why current will be high. Over time it will reduce. What will happen in the transient period is that the current in the damper winding, it will decay. This damper winding current will decay faster than the field winding current. Okay. So at this subtransient to transient period, what is happening is only the field current is going to be present. So the internal generated voltage will still be high, but not as high as it was when the damper winding current was also present. Okay. And by the time it is going to the steady state period, the current in the field winding is also decaying. So why the currents in the damper and field winding are decaying? Because it is a transient. They have occurred, the induced current is happening because of a transient, and a transient will die out with time, right? So you can write down, this is the first point: due to currents being induced in damper and field windings, right after the fault, the internal generated voltage will increase. Okay. So the next point will be, so the current in first few cycles will be very large, and this is called subtransient current. So this is often denoted by I double dash. Okay. Now after that, what happens? After the first few cycles, the current in damper winding will decay, while the current in field winding is not yet decayed completely. Okay, so why is that? This is because the time constant of damper winding will be usually smaller. So when time constant is smaller, it means that the response is faster. Okay, so the decay is faster. It will reach 0 faster. So this is because time constant of damper winding will usually be smaller than that of field winding. So this period is called subtransient period. Now in the next few cycles, induced currents in the field winding will decay. The current through this period is called transient current, denoted by I dash. This is called transient period. So in the subtransient period, damper winding current plus field winding current will be present. In the transient period, only the field winding current will be present. Okay, and then finally steady state is reached. Once the induced current in field winding decays, steady state is reached. Then what is this current called? It is the steady state current. The current is now called the fault current. Okay, just to avoid confusion, the fault current is now called steady state current, denoted by ISS. So what will this be equal to? ISS will be equal to the internal generated voltage divided by the synchronous reactance. Okay, so you can see that when a fault is occurring, the AC component will anyways be increased because it is being short circuited, but it will have an even higher value because of the currents in the damper and field winding. Okay, and in addition, because the current in inductor cannot change instantaneously, DC component is also being present. Okay, so that will lead to a very high current in the first few cycles. Forget about the steady state. In the first few cycles, that is in the subtransient period, the current is going to be very, very high. So you can note this point down. Therefore, fault current in first few cycles, that is in the subtransient period, is high because of the induced currents in damper and field winding. In addition, because the current in inductor cannot change instantaneously, the DC component also comes into picture. So the DC plus AC component is very high. Okay, this is in the subtransient period. After that, the DC component is also reducing as well as the AC component is also reducing. Okay. So for that small instant of time, we have to protect the equipment. When that amount of high current is flowing, we have to protect the equipment. So accordingly, we will choose the protective equipment, the circuit breakers and everything. Okay. Accordingly, the protective equipment should be chosen. Okay. Now, one important or two important terms here are subtransient reactance and transient reactance. So we often define these reactances in such a way that this is represented as X double dash. So this will be equal to the internal generated voltage divided by the subtransient current, and the transient reactance X dash is equal to the generated voltage divided by the transient current. Okay. So what is actually happening? The generated voltage is not the same as in the steady state period. It will be higher in subtransient period, but we define the subtransient reactance so that we can use the same internal generated voltage, but we can assume that the reactances are changing over the 3 periods. The reactances are changing. That's what we can consider instead of the internal generated EMFs being changing. Okay.